Well, our today's last speaker, it's sort of the local hero. That's why he can bring requisites that you don't want to take by train. But if you just can fetch them in your office, it's easy. So from the Institute of Solid-State Physics of the Technical University of Berlin, we will learn about fear therapy for electrons. So if you have ever been an electron and if you fear something, then listen carefully to Daniel Vajner.
What is this guy doing? Bringing this ladder. Ladies and gentlemen, welcome. I don't have a lot of jokes because I have a serious topic for you. Physicists and non-physicists, I have a confession to make. Before I came to this stage, I was really nervous. You could even say I was afraid. But that's okay if you're afraid and you do it anyway, because that's the topic today. And I want to take you back to the last moment of your life that you were maybe super afraid. Namely, the first time that you had to jump from such a high diving board into a pool. And I wanted to let you relive that experience, how you were standing there, looking up. It seemed so far away. Then you started climbing. The ladder was so long, your heart rate accelerating, your knees maybe shaking. You might get dizzy while you get higher and higher, and you go up, and you stand there, and you look down, the crowd looking at you in anticipation. What is this guy actually doing? And you stand there at the edge, you look down, and you ask yourself, should I actually really do this? And now you think of this feeling, and you know this is the exact feeling that an electron has when being in an excited state in a two-level system. Okay, we continue. A semiconductor quantum dot, you can picture it as an artificial atom in a solid-state system. So I brought you a fancy simulation. In the simulation, we take a laser pulse, we shoot it at that semiconductor quantum dot, and what happens is exactly what you learned in one of the first talks today. We create an electron-hole pair, a concept, a quasi-particle, we call them excitons, and since the semiconductor is surrounded by a different material, this exciton is confined to this tiny region, which means that the energy states can only be very specific if you occupy them, which means that if these two charges recombine and they are confined in this kind of region, which you can picture as a prison for charges, and they recombine, you get a single particle of light emitted, a single photon. And these single photons, they can be used for actual quantum applications, such as secure quantum communication or optical quantum computing. And I want to take you through the process of what the electron experiences. So imagine you're an electron. You are standing there, happily minding your business in the ground state, no one disturbing you, and then suddenly there's an excitation laser pulse. It takes you to the excited state, just like I was standing here with my knees shaking on the ladder. You suddenly get super afraid because you ask yourself, should I actually jump down? So the electron is hesitating, and the time it needs to jump down, it goes down exponentially typically, and we call that the lifetime of the electron. So we wait, and we have to wait so long, or maybe not that long, but still a significant time until the electron actually has the courage to jump down and we get a single photon. So I want to convince you that it's important to make that lifetime as short as possible. And for this, there are two reasons. The first one is we want as many single photons as possible. Imagine me standing up here, taking forever to jump, and there's 20 people waiting there. They also want to jump. This is not how you run a successful swimming pool. So if this electron, it will take forever to jump down. It means it goes up slowly and down slowly. We only get a single photon. But if we could actually convince this electron to go up and down very fast, we get a lot more single photons, which is good for our applications. The second reason is maybe less obvious, but if this electron is excited and in the excited state, there are other electrons in the vicinity, and the electron might interact with the other electrons, causing it to change its energy, so that the single photon actually has a different energy as well. But we don't want that, because for applications, we want all the photons to be identical, exactly the same. So if we convince the electron, when standing up there, to jump down very quickly, there's no time to interact with the other electrons, and therefore all the photons will be identical. So it all boils down to the question, how can we make the electron decay very fast? Or in other words, how do we take the fear away of the electron? How do we encourage the electron to jump down? And this is a question we ask ourselves in our research. And the first thing we learned is that there's actually a name for that. It's called catapedophobia, the fear of jumping from a high place down. So we try to cure that catapedophobia of the electron by all the standard methods. So we sent the electron on a vacation to let it relax a little bit, but it didn't help. So then we paid for therapy lessons of the electron. Also, that was not successful. So we got super frustrated and we tried hypnosis. But even hypnosis didn't help, so we experimented. We're experimental physicists, we experimented with, let's say, performance-enhancing substances for electrons, but even that didn't help. So we thought back to the situation of, let's say, an actual diver standing up here, thinking whether he should jump down there. And when you are up here, the pool down there actually looks pretty small. This is one of the main reasons why you're afraid. You're like, will I actually hit the water? I am so far away. So there's a very good trick that you can use, which is quite obvious. You just make the pool larger. Because if you make the pool larger, suddenly it doesn't seem that high. It doesn't seem that far away. So how can we make the pool larger? It's not that obvious. We cannot just make the semiconductor pool larger. So we use a trick. We don't actually make the pool larger. We just make the pool seem larger. And we do this by putting mirrors around the pool so that the reflection of the pool in the mirrors makes the pool seem larger. Now, there's an equivalent of that in our semiconductor quantum dot. And then, of course, the electron is happy. So the equivalent is that by putting these mirrors, we call them cavity, we actually increase the size of the pool, which means there's more space suddenly in the ground state in which our electron can jump. And this actually has a name. It's called Purcell effect, after this Nobel Prize-winning scientist. And the last question that remains, does this actually work? Because I can tell you a lot. And therefore, I want to show you actual data from the lab. And for this, we go 100 meters from here to our actual quantum optics lab, which is not that far. And we first look at the measured lifetime for the case of the planar quantum dot. This is a quantum dot, the situation where we have not increased the size of the pool. We don't do any tricks. There are no mirrors. And in this case, this is the lifetime that we measure. It goes down exponentially. It's on the order of 1 nanosecond. And now comes the important part. Now we put the mirrors. Now we increase the size of the pool. And suddenly, the lifetime looks like this. This is amazing, guys. This is not a simulation. This is actual data. This should be worth an applause. So what we see here is an increasement. We make it faster about 25 times, which for these type of quantum dots, with these type of structures, is actually a record value. And it means that we don't only get the 25 times more brave photons from the brave electrons, but we also get 25 times more single photons, which is amazing for applications. So this brings me to the end. With this, I hope I could convince you, even though there was in the beginning some complications, I hope I could convince you we need single photons for quantum applications. We get those single photons from semiconductor quantum dots, but we want them to have short lifetimes, which we can achieve by putting mirrors and playing a trick. And if you want to learn more, I have to sneak in some advertisement for the other DPG talks of this week, where you can learn more. And if you are ever in life in a situation, when you stand up here and you're afraid of something, you ask yourself, should I actually jump down? Then think back of the electron, how the electron did it. If the electron can do it, then so can you. Thank you very much.
Daniel, Vajner, thank you very much.